During a short circuit, grid resistance instantly drops to zero, a cable's insulation fails, and a violent plasma arc bridges the gap between live wires. With nothing holding the current back, an immense volume of upstream power rushes directly toward the break. It is a catastrophic surge, pulling energy from every connected source on the network. This graph shows what that surge actually looks like. The steady wave of normal alternating current spikes into a massive, jagged peak the instant the fault occurs. Engineers call this the peak short circuit current, or IP, and it hits within the first few milliseconds. But the first wave is worse than it appears. Because of the grid's electrical properties, a decaying direct current curve gets superimposed onto the alternating current. The entire axis of the wave is pushed upward, making that initial peak asymmetrical and vastly more destructive. This towering wave of current creates extreme electromechanical stress. The magnetic forces generated in that fraction of a second literally attempt to rip solid metal components apart from the inside. Survival of the grid depends entirely on intercepting this massive spike of energy before the surrounding hardware simply melts into slag. The primary defense against this energy is the circuit breaker. Inside a controlled chamber, heavy metal contacts physically pull apart, stretching and cooling the plasma arc until the circuit is severed. But there is a fatal flaw in this mechanism. Physical matter moving through space is simply too slow to catch that initial sub-transient peak current wave. The breaker cannot block the spike. It has to structurally endure the extreme magnetic forces of those first few milliseconds in order to eventually break the steady current a few cycles later. If that initial peak exceeds the physical rating of the breaker, the device warps. The contacts fuse together, the insulating medium is overwhelmed, and the plasma arc continues to burn. When the arc isn't quenched, the breaker itself violently explodes under the pressure. The short circuit remains active, dragging down the next upstream substation and cascading the blackout across the grid. The ultimate safety devices protecting our electricity are bound by a hard, unyielding physical speed limit. A modern city is built on thousands of these physical breakers, all linked together in a dense, interconnected web. This illustrates a network's fault-level design limit. An invisible ceiling, this red line, dictates the maximum short-circuit energy it can safely contain. Historically, grids had an empty buffer between baseline fault energy, shown in blue, and the hardware's explosive limit. Engineers call this gap headroom. Over the past 2 decades, there has been a massive global push to connect distributed generation, bringing thousands of local solar arrays and wind farms online. This creates a difficult paradox. Adding new generation adds potential fault current. Every time a new renewable source connects, base fault energy rises. It erases the historical headroom, pushing the level dangerously close to the design limit. By greening the grid with distributed power, we are inadvertently pushing our aging urban infrastructure right to the brink of self-destruction. The obvious question is, if we are hitting the ceiling, why don't we just install stronger circuit breakers? The answer comes down to source impedance. The total short circuit current rushing into a fault isn't determined by one single location. It is dictated by the resistance of the entire upstream network. To safely handle a higher fault current at one substation, you can't just swap out a single piece of hardware. The domino effect requires replacing the bus bars, digging up and upgrading the cables, and installing larger grid transformers. Upgrading the global infrastructure to support these higher fault levels is an economic impossibility, with estimates stretching into trillions of dollars. Utilities find themselves trapped. We cannot stop adding clean energy to the grid, but we absolutely cannot afford to rebuild the grid to survive it. With brute force upgrades off the table, electrical engineers have to rely on lateral thinking to cheat the fault level ceiling without replacing the network. Current stopgap measures include physically splitting networks to increase impedance. This lowers the fault current, but it reduces alternative power pathways, making the grid far more prone to widespread blackouts. They also install current-limiting reactors, which add resistance, but these reactors constantly bleed energy and cause permanent voltage drops along the line. Pacing quickens. The more advanced approach uses smart hardware like IS limiters. These act as explosive fuses that sever the connection in a fraction of a millisecond, actually beating the peak wave before it forms. This animation shows a superconducting fault current limiter in action. During normal operation, the material offers zero resistance to the current, but the exact millisecond a fault spike registers, the material instantly shifts state, heavily restricting the flow. These designs are brilliant, but they are still desperate reactionary measures, acting like bouncers trying to manage the chaos only after it starts. The most elegant solution removes the grid's physical limitations entirely, starting right back at the source of generation. Older synchronous generators blindly feed raw fault current into a short circuit, but modern Type 4 wind turbines sit behind full-size power electronic converters. Look at the schematic. When the turbine's computers detect the sudden voltage drop of a grid fault, they instantly throttle down their own internal semiconductor valves. The generator limits its own fault current contribution to barely above normal operating levels. It effectively refuses to participate in the surge. Returning to the headroom problem, this means we can connect virtually unlimited amounts of clean energy without raising the grid's baseline fault level. The survival of the future grid does not rely on installing thicker cables or pouring stronger metal. It relies on building an intelligent, reactive network capable of throttling its own